Hello, this is Jongwani from BatterMachine. I would like to introduce the battery machine learning framework. Batteries exhibit nonlinear and complex behaviors. In recent research, deep neural network models outperform traditional models like EKF or RLS. Domain engineers who specialize in battery technologies often lack familiarity with machine learning and neural networks. This gap makes it challenging to implement advanced predictive models in their work. For example, they understand battery data and system deeply, but it might be hard for them to program ML algorithms. On the other hand, machine learning engineers are skilled in developing complex models but often struggle with the nuances of battery data. Battery data and stage are quite different from typical ML tasks like object detection, natural language processing, or product categorization. Without domain expertise, ML engineers might misinterpret battery data, leading to suboptimal models. To address the challenges discussed previously, we developed a battery machine learning framework based on my prior research. This framework encompasses everything from feature generation to optimization of neural network models. Our research included experimenting with various features such as raw data, statistical features, and mixed features. These features were tested using 4 regressors to evaluate their effectiveness, as a regressor requires significantly less computational resource compared to deep neural networks. To identify the importance of each feature, we employed 4 feature importance techniques. We then optimized 7 types of neural network architecture using hyperparameter optimization techniques. These experiments were conducted over a period of 6 months. Through these experiments, we discovered that noise reduction and feature selection significantly impact model performance. We also observed that some architectures exhibit large variations in performance based on hyperparameters, while others showed stable results regardless of hyperparameter in terms of accuracy. Additionally, we identified which architectures are suitable for embedded systems and which are better suited for cloud environment in terms of training and prediction time. We have now implemented this framework with a web-based user interface to facilitate feature building, DNN model creation, verification, and validation. This framework is designed to support both academic research and industrial deployment of deep neural network models. I expect this web-based battery machine learning framework will dramatically reduce the effort required to build a feature, DNN model, and perform verification and validation. From the next page, I will explain how to use our web-based battery machine learning framework. For more detailed information, please refer to our recent publication. Users can see the data for all cells collectively or analyze specific cells individually. For instance, if a user wants to visualize the data of a particular cell, they can select cell visualization and generate a detailed visualization for the cell. This functionality allows for in-depth analysis and understanding of individual battery cell performance, helping in diagnosing issues and improving predictive models. Users can select the feature generation method, Users can specify the start cycle and the number of cycles based on their modeling requirements. For instance, if the number of cycles is set to 100, the end of life cycle can be predicted within that range. During the feature generation process, the framework automatically removes noise from the data, ensuring that the generated features are clean and accurate. This step is crucial for creating high-quality features that improve the performance of machine learning models. The framework allows users to select different regressors, such as random forest, gradient boosting, lasso, or XGBoost. By fitting the model, users can quickly see how well the features predict the target variable. This step provides immediate feedback on the quality of the features and help in refining the feature selection process. Users can determine the importance of various features using different methods. The framework offers multiple methods for assessing feature importance, including permutation, coefficient, tree importance, and sharp values. Effective selection of small but impactful features can reduce the model size and improve training and prediction times, which is particularly important for embedded systems where computational resources are limited. The framework supports 7 different DNN architectures from my previous research. Users can manually optimize values such as the number of epoch, batch size, activation function, learning rate, and loss function. This flexibility allows users to tailor the training process to their specific needs, enhance the performance and accuracy of the models. We have plans to support automatic optimization, including DNN architecture and parameters, without user involvement through hyperparameter optimization techniques used in my previous research. However, this feature is currently not supported due to exhausted computing resource. The framework then generates a comparison of model predictions versus true values as shown in the graph. This visualization helps the user quickly assess the performance of their models and identify areas for improvement. In conclusion, the integration of domain knowledge with machine learning techniques is essential for accurate battery state prediction. By addressing the challenges faced by battery domain engineers, we developed web-based battery machine learning frameworks to minimize unnecessary effort. This approach not only enhances the predictive capabilities but also accelerates the development process, leading to better battery technologies and applications. We are looking for one research organization and one industrial organization that are interested in using our prototype to enhance their customer requirements. Please feel free to reach out if you are interested or if you have any question about the topic or the demo.